Okay, here I've got a video on geometric mean. When you see the word mean, you probably have been taught to think average, which is true. A mean is an average, but every mean that you've dealt with up to this point has been an arithmetic mean, and I'll write that out. And that's the idea that if you have two numbers, A and B, you add them up and divide by the number of values. If you have three numbers, you add them up and divide by 3, so on and so forth. So that's an arithmetic mean, which is used a lot. In fact, it's used the most often, but we're learning about a different type of mean called the geometric mean. In a nutshell, the geometric mean is the idea that if I have two numbers A and B, I can find the geometric mean by multiplying them and taking the square root. If you have three numbers, you would multiply them and take the cube root. So that's the basic idea behind geometric mean. Just a real quick application. Let's say you were comparing two cities, City A and City B. I'm just going to make up this example, so hopefully it'll work out okay. And let's say that they're rated on cleanliness. I don't know how we're gathering this data, on a scale of 1 to 5. Okay? And then let's say they're rated, their traffic patterns or their traffic congestion. I don't know, I'm making up variables that you might judge as see. Their average commute. It doesn't matter what the variable is, but let's say that's done on a scale of 100. So this city has a score of 88. This city has a score of 59. Okay? So if you were trying to find the average of these two, if you wanted to calculate or include both the cleanliness and the traffic congestion of a city, I wouldn't want to average those, add those and divide by 2 to find the arithmetic mean, because this traffic congestion would have a much heavier weight than cleanliness would. And so this would be a perfect example where in order to count both variables a little more evenly, I would probably take the geometric mean. I would multiply them and take the square root to get my score for a city. But that's just a little background. Geometric mean, as we're learning it today, is going to be used to find missing side lengths in similar triangles. So I've got our first example here. What you're going to learn is, notice that I've got a right triangle, and it's right because I've got my little right angle here. So see my large right triangle, ABC, I'll label my vertices. And it's right, but I've also got an altitude drawn down. This is an altitude because it's perpendicular with this other side. And so what I've created by drawing that altitude down is 3 right triangles. ABD is a right triangle because it's got its right angle right here. BDC is a right triangle because it's got its right angle right here. And then obviously my large ABC is a right triangle because it's got its right angle. And what we'll learn about this, and this is the basic idea, is that this altitude right here, BD, is the geometric mean of AD and DC, meaning that X equals the square root of 6 times 3. So I'll multiply 6 and 3, I take the square root, so that's the square root of 18, and if we wanted to actually simplify that, I believe that would be 3 roots of 2. So it's a way to find this altitude height in a right triangle. Now, I've told you what the geometric mean is, and that this is the geometric mean of these two, but we don't know why yet. So let's look at this in the context of similar triangles. So I'm going to zoom out a little bit, and I'm actually going to erase this to give myself some room. And what I'm going to do is I'm just going to draw these 3 triangles. So let's start by, I'm going to draw a big triangle ABC. And these drawings are obviously not going to be perfect. But I'm going to label what I know. I'm going to label that this B is a right angle, and that if that's 6 and that's 3, that AC must be 9. Then let's draw our medium-sized triangle. And just so it's facing the same way, I'm going to reflect it and draw it down here. So I'm going to reflect it up so that D is the right angle on the top. So I kind of want these all facing the same way. And I've got my medium triangle. And let's see, this is going to be D, my right angle. This is still going to be A. But this B right here is going to be that angle. And then let's draw our third smallest triangle. Okay? That's going to be BDC. So once again, I guess I'll reflect it so they're all facing the same way. So B, D, C. And let's see, we know some side links here. DC is 3. BD is X, and I forgot to label it on my medium-sized triangle. We have that AD is 6 because it's shown right there, so I label it. And we have that BD is also X. Now, what we're going to find here is that these are 3 similar triangles. Okay? That color is getting washed out a little bit. Let me turn off the light and see if that helps. Okay, so I apologize if that was hard to see, but we have these 3 similar triangles. Now, I want to talk about why they're similar. Okay, I want us to understand why they're similar. I know that angle A is in both my first triangle and my second triangle. Okay, so I'm going to use a highlighter just to kind of mark those congruent angles because I think it's a little easier if we color code it. I also see that angle C is in both my initial triangle and my smaller triangle. And then all 3 triangles have that right angle. Now, think about what we know. If we look at just our first 2 triangles, they both have a right angle and they both have angle A. Well, that means they're similar by angle-angle similarity. Therefore, if these 2 angles, like if A is congruent to A and B is congruent to D, then C has to be congruent to B because they're similar. Then we also have the same thing for our first and third triangles. They both have the right angles B and D, so those are congruent, and then they both have angle C, so those are congruent. Therefore, my first and third triangles are similar by the angle-angle similarity postulate. So therefore, angle A must be congruent to angle B. Because we know if they're similar, all 3 angles are congruent. Now, obviously, I have 3 similar triangles here. Now that I have 3 similar triangles, let's just look at these last 2 and see if we can set up a proportion that would help us find X. I see that my corresponding sides are AD and BD, so I could set up a proportion 6 over X, and that's equal to the corresponding sides over here, X over 3. So I have a proportion that would help me find X. If I use cross products, I have that 6 times 3 equals X times X, or in other words, that 18 equals X squared. If I'm to take the square root of each side of this equation and solve for X, we have that X equals the square root of 18, or 3 square roots of 2. Now, look at what we've done. Isn't 18 the geometric mean of 6 and 3? So that's what I initially showed you. I showed you that this altitude right here would have a length that's equal to the geometric mean of these 2 sides. So that's why I can just do 6 times 3 and take the square root of my product to find that length. And hopefully this diagram illustrated it. Now, we're going to look at one last example. And here's our final example. Now, here, you're probably looking and saying, okay, well, we know that this side times this side square rooted would give me this altitude, but that's not even what we're looking for here. You could find that and use it to solve the problem, but what we're going to learn is there's some theorems based off of this geometric mean relationship right here, and we can memorize those theorems, but personally, I get bogged down in which sides I put into my proportion and things like that. So I believe that the easiest way to do these is just to set them up the same way we did this problem, where I draw the 3 similar triangles and just use proportions to find any missing sides. So let's do that again. I'm just going to label all my vertices so I can tell which sides correspond. And let's start with big triangle ABC. It's got its right angle there at B. And I've got 25 and X. Next, I'm going to do my medium triangle, and I'm going to reflect it because I want it kind of facing the same way. ADB, so D is my right angle. A will be there, and this will be B. And then the only side we know on this one looks like is AD. And so if the whole thing is 25, and then DC is 9, 25 minus 9 means that AD must be 16. And then I'm going to do my third side, or my third little triangle. And that's going to be D, B, C. The hypotenuse BC is X, and DC is 9. Now, let's see what we can do here. Once again, I'm going to mark all of my congruent angles in this figure. We know that angle A is congruent to itself. And I can pick a different color because angle C is congruent to itself. And I want to hammer home this idea that if I look at my first two triangles, they both have a right angle, so all right angles are congruent, and they both have angle A. So these two triangles are similar by the angle-angle theorem, or the angle-angle postulate, excuse me. Therefore, these last angles must be congruent. C must be congruent to B. And then I can use the same thing for my first and third, or really for my second and third at this point. But using my first and third, they both have a right angle, so that angle's congruent, and they both have this angle C, so the first and third triangles are similar by the angle-angle postulate. Therefore, we know that angle A must be congruent to angle B. So I've established that I have three similar triangles. I can now use proportions to find missing side lengths. I see that 25 over x equals x over 9. Once again, I can see the corresponding sides here. That's how I set my proportion. The hypotenuse over this leg is the same as the hypotenuse over this leg. So to solve this proportion, I'm going to use cross products, or in other words, find the geometric mean of those two numbers. 9 times 25 equals x times x. So I have that 225 equals x squared, and I'm going to take the square root of each side and find that, I believe that's 15, equals x. So that's how we found that x, this missing side length, is 15. Now, if you want, you can go home and Google, these different theorems for which side lengths are related by the geometric mean. But I think the safest way to do it is to set up your similar triangles. Once I draw the three triangles, it's important that I label the corresponding congruent angles so that I know which sides are corresponding for my proportion. Then I can just use proportions to find my missing side length. So that's basically what geometric mean is. It's the idea that to find an average, I can multiply my numbers and take a square root. And then we kind of went on a little journey to show why that's true for similar triangles. And then we did a third example that kind of showed how, while it's true for some of these other sides, instead of memorizing which sides have that relationship, it's easiest to me just to set up proportions and solve.